Time to analyze the first problem dealing with centripetal force, with the rock being whirled around in a horizontal circle. Horizontal is important. The thing about horizontal is we will ignore gravity. There really is no such thing as swinging something around in a horizontal circle. Gravity always affects it. But we will ignore gravity when we deal with horizontal problems. The other nice thing about horizontal problems is the force is constant everywhere. It doesn't change based on location like we will see in a vertical problem. So when we have to draw a picture, all we really have to do is analyze an object in a horizontal circle at one point. So let's look at something like this. Let's say here's the center of the circle. Here's our string and here's our rock. There's our rock, going to follow a path. Something like this, horizontally. So it's going to be whirled around this way. So how do we approach it? Once we know we have an object following a circular path, we want to examine this equation. Sum F equals FC. It's almost like sum F equals MA. All right. In other words, we know how to deal with the left side by summing forces. The only difference, the right side is FC. But it really kind of is an MA, because if you look at FC, it's a mass times an acceleration. So what really is, it's just a special MA. And that MA is centripetal force in this case. So we work right to left. We look at the FC part and we determine the form we want, either the linear or the angular form. We determine that by looking at either what is given or what we're looking for. We were told the rock was being whirled around at 1.88 revs per second, and that is an omega. Once again, know your units. So that means I'm going to choose this form, mr omega squared. Now I'm done with everything dealing with FC. I simply want to now just say, all right, pick the object and draw the forces acting on it. Don't draw FC anywhere. Just like we never drew MA on anything, we don't draw FC, which is MAC. Here's the rock. What forces directly act on the rock, and we only care about the radial path? Well, there is only one, and that's the tension in the string. The tension in the string acts inward. Ropes do not push on things. There is no force pushing that rock outward. That rock really wants to follow a straight line path, tangent to the circle, but the tension in the string pulls it so it does not. Remember, pulling it inward doesn't mean moving it inward. Just as it always has been, the direction of a force only tells you the direction of the push or the pull, not the direction of motion. So that is the only force. And we always call positive towards the center of the circle, because that's the direction of the centripetal force. So if we are to sum all the forces, all we get is this, T. So in this case, the tension in the rope supplies, which means is the equal sign, the needed centripetal force. So what do we have to do? We already know the numbers. M was 524 grams, or 0.524 kilograms. The radius was given as 1.22 meters. Omega, we can't use 1.88. Bad things will occur if you try. Look at the units, revs per second. It must be converted to radians per second. So make sure you don't forget revs per second, 2 pi radians per rev, and that's 11.8 rads per second. You have to put it in radians per second. Again, be very careful. And the equation says to square it. Make sure you do that. So you're going to end up with kilogram meters per second squared, because radians don't count. That's a Newton. And in fact, you get 89.0 newtons, and that's the tension in the string. So for this problem, the only force supplying FC is the tension in the rope.